All right, so our final segment for Chapter 7 on solutions, and it's going to be all about colligative properties. So we've talked about concentration, we've talked about making solutions, we've talked about um, solutions in stoichiometry. So the last thing is to talk about colligative properties. Now, colligative properties are properties that depend only on the number of dissolved particles. Okay, not what kind of particle. So we talked about electrolytes and non-electrolytes. We talked about strong electrolytes, weak electrolytes. Here, we're going to see a bigger effect from electrolytes, but the property itself does not depend on the type of particle. So non-electrolytes will contribute to colligative properties. Okay, so what are colligative properties? Well, these are the properties that change when we add a solute to make a solution. So for instance, putting salt in water changes the physical properties of the water because it's become a solution. So for instance, in wintertime around here, the trucks will run up and down the highway, and now what they do is they spray out a salt water solution onto the road, and that way when it snows, the snow won't be able to melt and freeze onto the concrete. It just melts and then goes away like rain. So it's going to be based on how much you add, but not what is added. So there is a component of it that is concerned with concentration, but it doesn't matter what type of compound it is that's in the solution. The effect of the electrolyte, the reason why they're more effective, it's going to be based on the number of ions produced. So for instance, if I dissolve sugar, for every one particle of sugar, I get one thing in the solution. But if I take table salt and dissolve that, I get sodium and chloride, and they act like individual particles dissolved in the water. So it's like a 2-to-1 effect rather than a 1-to-1. Now, the colligative properties themselves would be vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure. So these are the 4 things we're going to be concentrating on. Now, vapor pressure lowering and boiling point elevation actually go hand in hand. So as we think about a solution and how it's changing from a liquid to a gas, we're going to see how these 2 things play a part. Okay, so vapor pressure lowering. The introduction of a non-volatile solute will reduce the vapor pressure of the solvent in the resulting solution. So the first thing we have to understand is, what is a vapor pressure? So the vapor pressure of a non-volatile component is essentially 0. In other words, non-volatile means it's not going to go into a vapor readily. So like table salt, for instance, would be non-volatile. It wants to stay as a solid. And so its vapor pressure would be 0, which means it doesn't contribute to the vapor pressure of the solution. So what is the vapor pressure of the solution? Well, you have atmospheric pressure, and then let's say we have water. So the water, some of the liquid water wants to become a vapor. Okay? And if the pressure is right, then it will do that until pressure is met. Then once the pressure hits a certain point, that stops. Okay? No more water turns into a vapor. If we change that pressure, we can actually push it down so that more of the water stays as a liquid rather than becomes as a vapor, or we can turn up, and I shouldn't say turn it up, we could add to the pressure. So actually if the pressure goes up, that volatile solution wants to become non-volatile, so it wants to become a liquid. If the pressure goes down, so we pull a vacuum, then we're going to pull the vapor out of the liquid. Okay, so now the solution's vapor pressure is dependent on the solute mole fraction. Now that's just, a fancy way, a chemistry way of saying how many pieces are in there by a fraction. So like 5-to-1 or 3-to-1 or 5-to-40, whatever it may be, right? So the solution's vapor pressure is dependent on the mole fraction. So how many moles are in solution, not how many grams, right? So like sodium chloride, we would be looking at the mole fraction, not the number of grams of salt that are in there. And if that's not making a whole lot of sense, when we talk about boiling point elevation, sometimes the other view of boiling point elevation will make vapor pressure lowering make a little more sense. But for now, we're going to go on to freezing point depression. When you add a solute to a solvent, the freezing point goes down, right? The more you add, the lower the freezing point will get. Now, this is only going to work until you reach saturation. So now remember, if I'm putting a solid in liquid, as temperature goes up, so does the amount that can be dissolved. So conversely, if I go down in temperature, then I'm not going to be able to hold as much solid in solution. Okay. Now, again, examples of this would be salting the roads in winter. So as we put salt in the water is not able to make a uniform pattern and become a solid. Right now it's got these sodiums and chlorides that are kind of mixed in throughout, kind of breaking it apart, making it harder for them to get into an organized pattern. Okay, so that's how that's working. Another example might be making ice cream. If you've ever made ice cream, you're going to take salt, put that in into the ice water, and that way you're lowering the freezing point for the milk, so the milk can actually start to begin to freeze. The cream can begin to freeze. Now for boiling point elevation, when you add a non-volatile solute to a solvent, the boiling point goes up. This is because the vapor pressure has been lowered. Now, again, how do we make sense of this? So if I think about the particles of water in the pot, let's say, and I turn the gas on, turn my stove on, and I bring the water to a boil, what I'm doing is I'm giving the molecules energy. They're taking that energy and they're breaking free, right? They're breaking free from the liquid and becoming a gas. That takes energy to make that happen. Now, if I put salt in there, what's happening is now I've added an attractive force. So the water now sees the sodium ions and the chloride anions, and it's attracted to that. That means I'm going to need even more force to get over top of that in order to get that water to break free. So the water doesn't want to break free now because it's now attracted not only to the sodium and the chloride, but it also needed a certain speed to get up to begin with. So I've increased the amount of energy that's required for that water to begin to boil. Okay? The boiling point will continue to be elevated as you add more and more solute until you reach saturation. So again, we see that same idea. Now, where do we see examples of this? Well, cooking pasta with salt water. So whenever we go to cook pasta, typically we throw a bunch of salt in the water. We always think it's for flavor, or most of us, if we're honest, it's because that's what grandma did. But what grandma knew was that grandma she didn't grow up with a microwave. So if she wanted to cook something like pasta and she wanted to get it done faster, she would put salt in the water because she knew that was going to make the temperature warmer, hotter, and then more heat means I'm going to exchange more heat to the food, so that food item's then going to cook sooner, right? Another place we see it is antifreeze. So living here in Delaware, if you put water in your as your coolant, just ran straight water in your in your radiator, couldn't think of the word, in your radiator, then you run a risk both in the extreme winter and the extreme summer. In the extreme winter, the water could freeze, and we all know that ice expands, and that will rip your radiator open and cause it to leak. In the summer, it's because the water can't hold as much heat, right? The temperature is going to go up and it can't hold as much heat, which means then it puts more pressure on the radiator and will blow the cap off the radiator and we lose all of the water. We can't keep the engine cool. If we put antifreeze in, then that's going to lower that boiling point. By lowering that boiling point, it reduces the pressure that's coming off of that liquid. All right, the last topic we have that's a colligative property is going to be osmosis, but it's actually osmotic pressure, but we need to understand what osmosis is first. So osmosis is the movement of a solvent through a semi-impermeable membrane from a dilute solution to a more concentrated one. So here, the liquid is going to move across the semi-impermeable membrane in order to lower the concentration until it's the same on both sides. All right, so much like gas molecules were moving because of pressure, they wanted to lower pressure on one side or the other. That's what we're doing here. Okay, we're going to move solvent across the membrane in order to bring the concentrations closer to being equal. So what are semi-impermeable membranes? Of course, here we're targeting cell walls, right? We want to apply this to the medical profession. So we're looking at the cell wall. The cell wall, the water can slip back and forth. And of course, if I have a high concentration over here, then water will go this way. If I have a high concentration on this side, then all the water will go back that way. So unfortunately, my little video here, it doesn't seem to be working these last few years. But what happens here is I have sodium chloride on this side, nothing but water over here. The water will go through the membrane. This will lower the concentration on this side. And of course, all the water will continue to go from left to right until the concentrations are approximately equal. Okay, so that will be the goal of the water. Now, again, we just have to understand what osmosis is, but what we really want to talk about is osmotic pressure. Now, osmotic pressure is the pressure required to stop osmosis. So if we go back and look at this video, what I want to do then is apply pressure on this side and make sure that water stays over there. Okay, that's what osmotic pressure is. So the pressure required to stop the osmosis. Now, osmotic pressure could be equal to the concentration times RT, where M is the molar concentration, T of course would be Kelvin temperature, R is the gas law constant. We saw that before. Makes sense because we know that pressure times volume is equal to nRT, right? That's where that's coming from. We're not going to get too much into this, but that's where we're going to relate this to. So pressure, in this case osmotic pressure, would be equal to nRT divided by V. Now, again, conceptually, because I don't care about math for this section of it, all I care about is the concept. So conceptually then, here's what we have. I have pure water on this side. I have salt water on this side. Right now the tube is open, right? So it's open to the atmosphere. And so right now the only pressure that's being exerted is atmospheric pressure. So if I push go and let water do what water wants to do, all of the water will want to go to that side, right? So it's going to want to go from pure water over to the salt water. So we would see this level right here go up, right? So this water level would go up. What osmotic pressure is saying is, okay, well, I don't want to open this up to the atmosphere anymore. Now I'm simply going to put my hand on top of this. And what's going to happen? Well, this might still come up. It's just not going to come up as much, right? So now it's going to stop right in here because that head space is going to start to generate pressure. And as that pressure goes up, it's eventually going to come to a point where that force is greater than or equal to the force of the water coming across and adding to that volume. Okay. Now, if I actually add pressure, I can literally push all the salt water through and make it pure water. And if you've ever been on a cruise ship, that's exactly what they do. They don't actually carry water on the cruise ship unless you buy bottled water, but like to use the water in the bathroom or to get just drinking water in the kitchen or in the bathroom if you're just going to get water to brush your teeth. That water is usually obtained through the reverse osmosis. So we're actually going to put pressure on the side, push it through a filter, and turn salt water from the ocean into drinking water on the boat. Okay. Now, we don't really care about taking a cruise right now. What we care about is cells, and more specifically, what the conditions are inside the cell. So there's three conditions that are going to exist. The concentration can be the same on both sides of the cell wall. We call that isotonic. Okay. The concentration could be greater on the inside of the cell. That means we're going to have a hypertonic solution or a hypertonic cell or a hypotonic solution. So if the concentration is greater on the inside of the cell, it's a hypertonic cell, right? If you have a hypertonic cell, then you have to have a hypotonic solution. If the concentration is greater on the outside, we're going to flip those prefixes, right? So now we have a hypotonic cell because we have a hypertonic solution, right? And of course, here, unfortunately, my videos aren't working either, but we have crenation, which is water being drawn out of the cell. So what we would see here is that, so in crenation, where is the concentration, right? It's at a hypertonic solution. So is the concentration inside or on the outside, right? And so here, water is being pulled out of the cell because it's concentrated out here. So we have a hypertonic solution. Right, so that means what's going to happen is the cell itself is going to shrivel down and become worthless to us if this concentration is too high. On the other hand, it says hypertonic solutions, but really this one's going to be a hypotonic solution. And so now what we have is the concentration on the inside. The water is going to go inside to the cell, and the cell is going to blow up like a balloon. And eventually, if it's too much, then it will just pop. right? Just like putting too much air in a balloon. All right, so that ends chapter 7 for us, colligative properties being the last segment here. If you've got any questions going forward, make sure you get a hold of me, come to my student office hours, or schedule some time with me if you're unable to make it to the hours that are already set. Hopefully things are going well. And again, if you're having any troubles, make sure you get in touch with me. Plenty of practice problems. I can give you websites. If you just want to do practice problems, let me know. I'd be more than happy to help you in any way I can. All right. Talk to you soon for chapter 8.